This is part 10 of a series on generative adversarial networks. In this video, we will look at the Wasserstein GAN with gradient penalty, WGAN-GP. This video was produced in Korean and then translated into English. The audio was generated via AI, text-to-speech. In the previous two videos, we looked at the Wasserstein GAN, WGAN. In this video, we will look at the WGAN-GP model, which is proposed to improve the shortcomings of WGAN. First, let's compare the differences between WGAN and WGAN-GP. Next, let's look at the problems that can arise when using weight clipping in WGAN. And let's look at the WGAN-GP algorithm. Finally, let's implement a WGAN-GP model using Keras. The objective function of the original WGAN we looked at in the previous video is as follows. WGAN uses weight clipping to enforce a one-Lipschitz constraint on the critic, which can lead to undesired behavior. Even the authors of the original WGAN paper mentioned that weight clipping is a clearly terrible way to enforce a Lipschitz constraint. If the clipping parameter is large, then it can take a long time for any weights to reach their limit, thereby making it harder to train the critic till optimality. To improve this problem, Ishan Gulrajani et al. Introduced WGAN-GP in their paper, Improved Training of Wasserstein GANs, in 2017. The objective function of WGAN-GP is as follows. The authors of this paper proposed an alternative to clipping weights, penalize the norm of gradient of the critic with respect to its input. This method performs better than standard WGAN and enables stable training of a wide variety of GAN architectures with almost no hyperparameter tuning. Section 3 of the paper contains a general discussion of the difficulties with weight constraints. Let's read the first paragraph of the section. We find that weight clipping in WGAN leads to optimization difficulties, and that even when optimization succeeds, the resulting critic can have a pathological value surface. We explain these problems below and demonstrate their effects. However, we do not claim that each one always occurs in practice, nor that they are the only such mechanisms. The first row of this figure shows the contour plot of the value surfaces of the WGAN critic trained to optimality on toy datasets using weight clipping. The first figure shows a dataset consisting of 8 Gaussian distributions that is mainly used in this series. And the second row shows the contour plot of the value surfaces of the WGAN-GP critic using gradient penalty. The contour lines in the figure above are simpler than those in the figure below. Implementing a K-Lipschitz constraint via weight clipping biases the critic towards much simpler functions. Therefore, critics trained with weight clipping fail to capture higher moments of the data distribution. The authors of the paper observed that the WGAN optimization process is difficult because of interactions between the weight constraint and the cost function, which result in either vanishing or exploding gradients without careful tuning of the clipping threshold C. To demonstrate this, they trained WGAN on the Swiss roll toy dataset, varying the clipping threshold C as follows. and plot the norm of the gradient of the critic loss with respect to successive layers of activations. Both the generator and the critic have 12 layers. This figure shows that for each value of C, the gradient either grows or decays exponentially as we move farther back in the network. WGAN-GP results in more stable gradients that neither vanish nor explode, allowing training of more complicated networks. Weight clipping pushes weights towards two values, the extremes of the clipping range, unlike gradient penalty. Next, let's look at the WGAN-GP algorithm. As we saw in the previous video, the Wasserstein 1 distance can be expressed as follows. F is a neural network with a one-Lipschitz constraint, called critic. X comes from the real data distribution, and Y comes from the generated data distribution. There's a one-Lipschitz function f star, which is the optimal solution of the critic. If f star is differentiable and xt is as follows, then the following equation holds. Xt is an image at any linear interpolation between the real image x and the generated image y. The expression in square brackets tells us that the gradient norm of f star with respect to xt is 1. F star has gradient norm 1 almost everywhere under PR and PG. The probability that the gradient norm of f star is 1 is 100%. The L2 norm of the gradient of f star with respect to xt is less than or equal to 1. A proof of this is given in the appendix of the paper. Now that we know the properties of the optimal critic, we can understand the WGAN-GP algorithm. Update the critic network n critic times, and update the generator once. Sample real data x from PR, and sample random noise z from PZ, and sample a random value epsilon between 0 and 1. X tilde is the output of the generator, which is the generated data. This corresponds to y in the proposition 1 on the left. X hat is a linear interpolation between the real data x and the generated data x tilde. This corresponds to xt in the proposition 1 on the left. There are many linear interpolation images on this line, but we are randomly sampling one of them. We use these outputs from the critic network to compute the loss. The lambda is the gradient penalty coefficient. This is the penalty term. This is the loss of the existing WGAN. The more the L2 norm deviates from 1, the larger the penalty applied. This allows us to impose a one-Lipschitz constraint on the critic without clipping the weights. The authors of the paper encourage the norm of the gradient to go towards 1, which is a two-sided penalty, instead of just staying below 1, which is a one-sided penalty. This would penalize gradients larger than 1, but not gradients smaller than 1. The authors say that the two-sided penalty version seems to perform slightly better. This process is repeated m times. M is the batch size of training data. Update the critic network using gradient descent or the atom optimizer. Next, we update the generator in the same way as the standard GAN. Now let's implement a WGAN-GP model in code. generate a dataset consisting of 8 Gaussian distributions arranged in a circle like this. This code is very similar to the code we used previously in WGAN. Let's just look at the parts that have changed from before. Let's write a custom class to create the WGAN-GP model. The inputs to this class are D, which is the discriminator or critic, G, which is the generator, and GP lambda, which is the gradient penalty coefficient. The authors set the default value of lambda to 10. We use the atom optimizer to update D and G. Next, we write a function to compute the loss of the discriminator. The input X and Z are the real data and random noise, respectively. GZ is the output of the generator for Z. DX is the output of the discriminator for X. And DGZ is the output of the discriminator for GZ. M is the batch size of training data. Next, we compute the loss with the gradient penalty applied. Compute the loss as shown in algorithm 1 on the previous page. This has already been covered in detail, so I will skip the explanation. Next, we write a function to compute the loss of the generator. This is the same as what we did in standard GANs. We define a list of metric objects for the discriminator loss and the generator loss. Next, we define the train step method. This is also identical to that of a standard GAN. Update the discriminator 5 times and update the generator once. We create and compile the WGAN-GP model. We set the GP lambda to 0.1. Finally, let's write some code to check the results. This code is also the same as before, so I will skip the explanation. Let's take a look at the results. The loss history of the discriminator measured during training is as follows. After 1,000 iterations, the loss converges to almost 0. The loss history of the generator measured during training is as follows. After 1,000 iterations, the loss also converges to almost 0. After 100 epochs, the distribution of fake data is as follows. The red dots are fake data G of Z generated by the generator, and the blue dots are real data X. After 200 epochs, the distribution of fake data is as follows. The fake data is now a little closer to the real data. After 1,000 repetitions, the fake data became very similar to the real data. Let's run this code. The results are as follows. So far, we have looked at the WGAN-GP model. In the next video, we will look at dual discriminator GAN, shortly D2 GAN.